In this question, we've got an interesting summation where we are alternatively minusing or adding to, consecutive numbers, essentially. So I think a good shout is, although we're given S5, is to write down just the first few. So S1 is going to be 1, and then S2 is going to be 1 minus 2, which is minus 1. S3, we then do 1 minus 2 plus 3. We can just add 3 onto that last one to give 2. We can kind of see a pattern emerging. S4, we're just going to we're going to do 1 minus 2 plus 3 and then minus 4. And that's going to equal minus 2. And you can sort of start to see that the pairs are equal to minus 1. And that's worth making a note of, actually. We've got to make sure we're justifying results. S5, well, it's given above, but I'm just going to write it down again. Okay, so it's just going 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, and so on, it seems. And then the main question we're asked is, for what values of a does this hold? So we're going to have to try and write down a general expression here. But we can see that there's like the jump between being positive and being negative. And the thing is, for the odd numbers, we get positives, and for the even numbers, we get negatives. So when I did this question, I considered them separately. I said, consider S of 2n, because that will necessarily give me an even number. And then, but we're going to get 1 minus 2 plus 3 minus 4, etc. And the very last term is going to be 2n plus 2n minus 1 minus 2n. And essentially, we're going to get lots of minus 1 pairs. And in fact, we're going to have n lots of minus 1 pairs. When I say minus 1 pairs, I mean two numbers that sum to minus 1. It's a little bit misleading, isn't it? N lots of pairs that, I should write that exactly. N lots of pairs that sum, that add to minus 1. So overall, we're going to get n times minus 1. We're going to get minus n. Now, I've got to be honest, when I originally did this question, I just wrote it straight down. It was just intuitive that it's going to be minus n, but the Olympiad expects you to justify it. And so I feel like this is needed. I should also just add that n is like um, it's, it's a counting number. It's a natural number. Um, or you could just write that n is an integer, but it's greater or equal to 1. This is like a nice bit of notation to say that n is a counting number, 1, 2, 3, and so on. And so we're going to get, like, basically we're looking at the even numbers. Okay, good. So, we can just test it. When when n is 2, we get s of 4, and that would be minus, sorry, when n is 2, we get s of 4, and that's going to be minus 2, and that works. So all good. Right, let's have a little look at s 2n minus 1. I'm going to put a minus 1 here because I'm again going to consider n being a counter number. So this will work for s of 1. Now, this time, I'm going to be getting, sorry, I've kind of just need to move this. I'll leave it. I'll leave it out because I've already defined what n is. So I'm going to be getting 1 minus 2 plus 3 minus 4, etc. But then I'm going to get 2n minus 3 minus 2n. Actually, I should put this in a bracket, 2n minus 2. But then my last term is going to be plus 2n minus 1. And this time I'm going to get lots of pairs. I've got my minus one pair, minus one pair, minus one pair. Sorry, this one here. Except here. But I do still have a minus one, actually. That's quite important. So I'm going to get n lots of minus one, just like before. But then I'm going to add on this extra 2n. And overall, that's going to give me minus n plus 2n, which gives me n. Okay, now again, when I did it, I did not justify it enough. I just wrote down that it was n, because you can kind of just look at the pattern, but we need to be able to justify it. And hopefully you're happy that that's what I've done here. Okay, and the solutions, they do not go into they just say that A and B are even, but I quite like the idea of just, getting an expression for any even number and any odd number. So now let's look at this expression, SA plus SB plus SAB, and when is it equal to 1? Right, let's look at some different cases, because it depends on whether A and B are odd or even. So, case 1, A and B are going to be even, which implies, okay, actually that means implies, maybe I won't use that notation here, um, A and B even, so A plus B will also be even. You can assume that, so we don't need to prove that or anything. Then all sums will be negative, because we've literally just shown a minute ago that we get minus n. So no solution. Okay, let's look at case 2, and A and B odd. This time we've also got A plus B even. Okay, this could work. So then we could write down the S of 2n minus 1. That's going to be my A, plus S of 2m minus 1. Okay, it's a different letter here, but it's just going to be a different odd number. That's going to be my B, plus S of 2n minus 1 plus 2m minus 1. And we're interested in this equaling 1. Now, from above, we have this result. Remember, it's equal to n. And then this one, for a similar way, is going to equal m. So I just need to worry about this one here. And it's going to be S of 2n plus 2m minus 2, which is going to be S of 2 lots of n plus m minus 1. So we see that we get an even number here. Now remember, when it was s of 2n, and it's getting quite technical, when we got s of 2n, it was minus n, which means that this thing here, right, using this result, is going to be minus n plus m minus 1. Okay, this is now just my n from before, so it's minus that, and that's equal to 1. So I can write down that n plus m minus n minus m plus 1 is equal to 1. And this is true for all values. True for all values of n and m. What this means is if a and b are odd, then s of a plus s of b plus s of a plus b is always 1. Okay, that's quite a nice result, and we've proven it. Just got one more case. So case 3, sorry. We're going to say A even and B odd. Of course, you could have it the other way round, but because of the symmetry of this problem, once we get a solution for A, we'll also get a solution for B. Like if A's, if this was odd and this is even, then we can just swap them round afterwards. So it's not going to be a different solution. Right. So now we're going to get S of 2n plus S of 2m minus 1. Remember, this is my B and this is my A, plus S of, it's going to be, okay, I'll write it in full, 2n plus 2m minus 1 equals 1. But this thing here, by the way, this is A plus B. This thing is going to be 2 lots of n plus m minus 1. Clearly, I should have said A plus B is also going to be odd. Right, then here, I'm going to get minus n, like before. Here, I'm going to get m. And here, I'm actually going to get n plus m. So minus n plus m plus n plus m is equal to 1. These cancel. 2m equals 1. M would have to equal a half. Okay, we reject this because m is an integer. In fact, actually, that's not the problem, is it? We'll just get s of 0. So not allowed. Sorry, what am I doing here? 2m, yeah, 2m minus 1 is equal to 0, and that would be my A. And that would be my B. Oh, sorry, I'm making a mess of this here. B would equal 0, not allowed. So there are no more solutions. Okay, that is my attempt at doing this question. I think it's pretty good. The solutions do not split it into 2m, 2n and 2n minus 1 and so on, but I quite like the way that I did it here. I think I personally made it a bit clearer for me, but do have a look at the official solutions as well. Quite a technical question, all right? Quite very awkward, I think, for question 4, but I hope it makes sense. And as always, well done on your efforts.